Okay, in this video we're going to talk about SHSAM and some of its limitations, but I'm also going to, later in this video, I'm going to explain some like best practices that I like to use. So two of the big limitations of SHSAM, all modeling programs have their limitations, and as an engineer you just need to decide, where are the limitations and how can I minimize the amount of uncertainty in my calculations. Well, with SHSAM, the limitations are with snowfall and with sediment. So first off, with the snowfall, SHSAM is unable to model snow runoff. Basically, in areas that get a lot of snow, a decent amount of runoff that occurs, that storm sewers experience, occurs during kind of like snow melt time periods of the year when it snowed, it's starting to warm up, and that snow starts to melt, and water is kind of trickling into the storm sewer. SHSAM is not able to model that. That's just one of the limitations that we have to deal with. But this isn't a big problem, obviously, if you're in a climate that doesn't experience a lot of snow, but if you are in a climate that experiences a decent amount of snow, it's important to just think about that and think about what that means for the uncertainty of your project. Second off is sediment. And if you watched the video where I run a simulation, one of the things that you have to tell SHSAM two different things about sediment. What is the particle size distribution? So how coarse or fine is the sediment? And then the second is influent concentration. How much sediment is going into your device during storms? SHSAM isn't able to vary sediment influent concentration throughout a storm like it would be in real life. SHSAM just keeps that concentration static throughout the duration of storms. So some ways that I try to minimize this, minimize the sediment aspect, is I try to do sensitivity analysis. I try to run simulations with different particle size distributions that I think could be on my site, and then I kind of, what is the range of performance between those different particle sizes. Another thing that I do is I vary how much sediment is, I vary the influent concentration. I do the same thing. I put in some low values, and I put in some high values, and I see how it affects my device. So let's open up Excel here. I'll kind of show you how I address these things. Whenever I'm running a simulation, I like to build up a little spreadsheet like this. And basically I have test number 1 through however many I want to do. And I enter in all of the inputs that I put into SHSAM. I just kind of label them out in this spreadsheet. So in SHSAM I have 7-acre watershed, 85% impervious, and so on. Well, in this test, I'm varying particle size distribution. So for this one, I set it at Jano Mead, which is kind of an urban stormwater distribution in the Twin Cities area. But then for test 2, I keep everything else the same, but then I vary the particle size distribution. I make it NJCat. And then for my third test, I make it NERP. Everything else stays the same. So let's run a couple of simulations here. Let's make this the size you guys can see. Okay. Let's burn through this real quick. Set up my root folder. I want to test the SAFL baffle. No bypass. Happy with those sizes. Golden Valley. Okay, so my first particle size distribution was Jano Mead, like in my spreadsheet. Now, what were my values for the watershed? So I had 7 acres, 85% impervious, about 1,000 feet of hydraulic length, 2% slope, and 75 for the curve number of the pervious. Finally, I picked the temperature that's right for my area. Yeah, St. Paul, Minnesota. influent concentration, I have that set at 100 milligrams per liter. Okay, I'll run the model. Okay, I go up into Tools, Output Data, click on the Summary, and I scroll all the way down to the bottom, and I can see the summary results from the simulation. So I'm going to take all of this, and my spreadsheet's already waiting for these columns, so I'm just going to hit Control-C, copy. I'm going to paste those in my spreadsheet. Center them. So yeah, I mean, total load removed, removal capture, or removal efficiency, and then these are the dimensions of the system. Okay, so next one. So now we're going to try NJCAT. So this is where SHSAM's useful. So I just click out of this Output Data to window, and now everything else is still the same in my input data. Now all I do is go to tab 5, particle size distribution, and I go down to NJCAT. That's it, and then I hit run model, hit OK, go back up to Tools, Output Data, scroll down, and load this into the next part of my spreadsheet. Okay, and what's our final one? NERP. Alright, particle size distribution, NERP. I think you guys are getting the idea here. It's really easy to run a good number of simulations with SHSAM back to back if you kind of plan out what you're testing between simulations. Oops. Okay, let me grab that. Okay, so now I have all of these different values, and what I set up is a summary spreadsheet, and this is where I can compare all of them. So I'm going to say, I care about the removal efficiency for my test number 1. Okay, so I like that. Test number 2. And test number 3. Okay, so you can see that the Saffel baffle did a pretty good job at capturing, I guess this is all relative, it depends on what your goals are for your site, but the Saffel baffle did better at capturing JANO-MEAD, urban watershed, or urban stormwater particle distribution data versus NJCAT, where it captured slightly less. So let's say that you're looking at this 6-foot diameter, 6-foot deep model, captured 16% of JANO-MEAD, but it only captured 11.5% of NJCAT, only captured 1.5% of NERP. And that's really a function of how these different particle size distributions compare to one another. JANO-MEAD is the most coarse, NJCAT's middle compared to these two, and NERP is generally viewed as a finer particle size distribution. So I like to do that, and then I throw this into a report and send it to whoever wants it. So you can see here, in this case, I've varied Saffel baffle particle size, but I could do this again for influent concentration or any other variables that I feel are unknown or uncertain in my analysis.